Today we discuss theorem 4.18. Theorem states that for square free d strictly less than minus 11, the ring of integers of q of root d, ring of integers O of q of root d is not Euclidean. The last class we have already discussed that for the values of d is equal to minus 1, minus 2, minus 3, minus 7, minus 11, we have O contained in Q of root D are Euclidean. Okay. In this case, the Euclidean function was phi of n is equal to, or phi of x equal to, or phi of a. I'll write phi of a is equal to norm of a. This was the Euclidean evaluation in that case. In all cases, these are the Euclidean evaluation. So once this norm is a Euclidean evaluation on this D, on this O, we can say that O is norm Euclidean. Norm Euclidean. So we have proved that for these values, these are Euclidean domains. In this theorem, we will prove that for d is less than minus 11, of course this d is a square free integer, square free, which is less than minus 11. We have q of d, ring of integers of q of root d is not a Euclidean domain. So we will prove this by method of contradiction. For if possible, let us assume this O be the ring of integers of q of root d, and suppose that this O is a Euclidean domain, or there exists a Euclidean function phi. Okay, suppose there exists such function, then we will get a contradiction. If this exists, choose alpha such that alpha not equal to 0. Choose an element, non-zero element of O, and that is not a unit. So I collect this alpha in such a way that alpha is always a non-zero quantity and alpha is not a unit, and phi of alpha is minimum among all the elements of O. So this is the choice of this alpha. Now, if you choose any other element, beta belongs to O, using this evaluation, you can get this alpha is equal, or beta is equal to alpha times gamma plus delta, with the property that this delta equal to 0 or phi of delta is less than phi of alpha. But we know that the choice of alpha says that phi of alpha is minimum. Therefore, this never happens. So the only possibility is d equal to 0. Okay. So the only possibility is this d equal to 0. And whenever this happens, phi of d is less than phi of alpha. So we can say that this d never be an element with this property. Yeah. So from this you can write this delta is a unit. That means the choice of alpha says that this never happens for a non-zero, non-unit delta. So whenever we write beta is equal to alpha, gamma plus delta, then we have only two possibilities: delta equal to 0 or delta satisfies this condition. A non-zero non-unit never satisfies this. Okay, so these two statements imply that either this delta is equal to 0 or this delta will be a unit. So this is the only possibility. Clear? Then we can get this delta equal to 0 or delta is a unit. For d is less than minus 11, it is easy to see that the only units, we already proved in the beginning of this chapter, the units in q of root d are plus or minus 1. The only possibilities for units in q of root d are plus or minus 1. So this again reduces to this delta equal to 0 or this delta will be plus or minus 1. So these are the only possibilities for this expression. Clear? So whenever you consider a beta belongs to O, you can write it as beta is equal to alpha gamma plus or minus 0 or plus or minus 1 or 0 uh, corresponding to this delta. So this implies that we know that this element is obviously element of ideal generated by alpha. Okay, so you can write it as beta beta plus ideal generated by alpha is for this coset we have only two possibilities, plus or minus 1 plus ideal generated by alpha, or you can write 0 plus or minus alpha. Okay, these are the only possibilities. So we rewrite this expression in this manner. We write this as beta congruent to minus 1 comma 0 or 1 mod alpha. This means that beta plus ideal generated by alpha has only three possibilities: minus 1 plus ideal generated by alpha, 0 plus ideal generated by alpha, or 1 plus ideal generated by alpha. That means the only possible cosets of this ideal generated by alpha is 1 plus ideal generated by alpha, minus 1 plus ideal generated by alpha, or 0 plus. These are the only possibilities. So these are the only possibilities means we have the cardinality of this quotient group O by ideal generated by alpha is always less than or equal to 3, because this contains only 3 elements. Okay, at the most 3 elements, so we can write it as the cardinality is always less than or equal to 3. That is obtained here. Now we need to get two references. One is theorem 1.17 and one is theorem 2.16. In 2.16 it states that this O is a free abelian group of rank n if K is a number field of rank n. So in this case we have considered quadratic number field. So K is this is a number field of rank number field of degree 2 over Q. Then you can get this O is a free abelian group of rank 2. This is theorem 2.16. In theorem 1.17 it states that how we get the cardinality of this. Okay, so that is two theorems that I will prompt for you. This is our theorem 2.16. Every number field K possesses an integral base and the addition group of O is free abelian group of rank n equal to the degree of K. This is what we called the theorem 2.16. This is theorem 1.17. In this theorem, it states that G be a free abelian group of rank R and H is a subgroup of G. Then G by H is finite if and only if ranks of G and H are equal. When we consider in our situations, we are considering G as the O and alpha, the ideal generated by alpha as H. Okay, we need to consider in our situation we are considering instead of G we have O, and instead of H we have the ideal generated by alpha. So we already proved that the cardinality of O by ideal generated by alpha is less than or equal to 3. So we can get this is finite. So using this theorem we can say that H is a free abelian group of rank 2. That means it has a basis of the form, or its basis contains exactly 2 elements. Okay, so when you consider in ideal generated by alpha instead of this H, we can say that ideal generated by alpha has a basis of order 2. So and this theorem, this statement says that using the basis of this G, we can get a basis for H. Okay, so in that case, this is the idea here. If x1, x2, xr and y1, y2, yr be the basis for G and H respectively, then we have yi is equal to this. Okay, so using this idea you can get a basis for ideal general by alpha using the basis of q of root d. It is obvious that the base of q of root d is 1 comma root d. Okay, so one thing you should remember is here we have g as o. Okay, so first we will write the basis for o. Using that basis we will write the basis for ideal generated by alpha. Okay, this is the way we refer this theorem to our present theorem. So first we consider the basis of O. We know that O is the free abelian group of rank 2. Then we need to consider O first. So O can be classified in two cases. One is D is congruent to 1 mod 4 and D is not congruent to 1 mod 4. These are the two cases. So in this case we can say that if D is congruent to 1 mod 4, a ring of integers of q of root d is classified as z of 1 by 2 plus 1 by 2 root d, and in this case we can write that is ring of integers O. This O is equal to z of root d. These are the two cases. Okay, so if you consider D is not congruent to 1 mod 4, we can easily get the basis of O as 1 comma root d. So these are the bases. Using this basis you can get the basis of ideal generated by alpha. Okay, so in order to get the base of this you need to multiply this with alpha. So this will be alpha comma alpha root d. Again these two elements are multiples of alpha, so these are elements of ideal generated by alpha. We know that alpha and root d are linearly independent in some sense, so you can get this is the basis for alpha. Now using this is the basis for our h in theorem 1.17, and this is the basis for g. Okay, using these two bases in that theorem we can take it as x1 x2 and this is our y1 y2. So using these two quantities you can find the cardinality of g by h. Okay, here we need to get the cardinality of this quotient group O by ideal generated by alpha. We know that is always less than or equal to 3. Okay, so in order to evaluate this we need to write the modulus of the determinant of some matrix. So this matrix is nothing but the transition matrix, determinant of the transition matrix. Okay, so that is when you consider this is alpha and this is alpha root d, in case d is not congruent to 1 mod 4, then this alpha is a plus b root d, then any element of z of root d can be written as a plus b root d. Then alpha root d will be when multiplied with root d you can get the first term as b into root d, that is db plus a root d. These are the elements. So first you write this alpha a plus b root d as a linear combination of 1 and root d. These are the basis for g. So this is 1 into 1 into a plus 1 into b into root d. Okay, so I'll write it as I'll write it as 1 into a plus this will be root d into b. Okay, and we'll write this db plus a root d as the coefficient of this one is db times 1 or 1 times db, both are same, plus this will be root d times a. Okay, so this constitute the transition matrix. Sorry, this is our a. Then this constitute the basis 1 root d. Then the transition matrix will be matrix a b d b a. Okay, This will be the transition matrix. Then finding the determinant of this, you can get the cardinality of O by this. So determinant of this is, we can write it as A square minus DB square. Okay, so this is nothing but norm of A plus B root D. Okay, so modulus of this determinant is nothing but modulus of this. So we can get this is nothing but our cardinality of our O by ideal generated by A. So O by ideal generated by not A, ideal generated by alpha equal to cardinality, sorry, modulus of norm of A plus B root D. Okay, so this is the cardinality of this one. We know that this is always less than or equal to 3. So this is always less than or equal to 3. In the next case, this is the case when D is not congruent to 1 mod 4. In the case when D congruent to 1 mod 4, we need to construct a basis for alpha, basis for this O ideal generated by alpha using the basis of this one, because this is in this case D is congruent to 1 mod 4. We have Z O as Z of 1 plus 1 by 2 plus 1 by 2 root D. For that we consider a basis for Z of 1 by 2 plus 1 by 2 root D as 1 comma 1 by 2 plus 1 by 2 root D. This is the basis for O. Then using this you can write a basis for ideal generated by alpha, that is alpha comma alpha by 2 plus alpha by 2 root D. This is the basis for ideal generated by alpha. Then we need to write, if we choose an arbitrary element alpha as A plus B 1 by 2 plus 1 by 2 root D. This is an arbitrary element. So first we write alpha, and alpha is this. Okay, so alpha in this manner. Then what is alpha by 2 plus alpha by 2 root D? So that is obtained by, so I'll write the next one, alpha by 2 plus alpha by 2 root D. That will be this by 2, that is A by 2 plus B by 2, this bracket, and alpha by 2 plus root D, that is this is 1 by 2 plus 1 by 2 root D. So plus we have next we have alpha by 2 root D. So this quantity times root D. So that will give the expression A by 2 plus A B by 2 half plus half root D. Okay, plus this quantity, this whole quantity into root D. Okay, so or you can write this alpha by 2 plus alpha by 2 root D. So that will be this quantity into root D. So A root D by 2 plus B root D by 2 into this bracket. So this is the expression for the second element, alpha by 2 plus alpha by 2 root D. So using this alpha and this, you can write this transition matrix. Okay. On the other way, there is some easiest way. On the other way, we can think of a general element of this Z of, we already discussed it in the previous cases, this 1 by 2 plus 1 by 2 root D as. Then what is the easiest way? Easiest way is to first write our O as Z of 1 by 2 plus 1 by 2 root D. This is the set of all A plus B times 1 by 2 plus 1 by 2 root D. So clearly this is A and B are Z, elements of Z. So the clearly 1 comma half plus half root D is the basis for O. Okay, using this we can get the basis for, I'll write it as basis for ideal generated by alpha. So the basis is set of all alpha comma alpha times 1 by 2 plus 1 by 2 root d. Now an arbitrary element of this z of 1 by root d plus 1 by root d is a plus b times half plus half root d. Then if we take alpha in this manner, then what is alpha times this? Alpha times 1 by 2 plus 1 by 2 root d is a plus b 1 by 2 plus 1 by 2 root d times the same quantity 1 by 2 plus 1 by 2 root d. When you multiply this, you can write, I'll write a simple expression, a times 1 by 2 plus 1 by 2 root d and square of that, b times square of this. What is the square here? 1 by 4 plus d by 4 plus 2 times this. 2 times 1 by 2, 1 by 2 root d. Okay, I'll rewrite this is equal to a times 1 by 2 plus 1 by 2 root d, and I'll write this is equal to plus b times. So when we multiply this, you can write it as b by 2 minus b by 4. The first term is b by 4. B by 4 can be written as b by 2 minus b by 4 plus bd by 4. This is the second term, and the last term will be, you can cancel this two, then last term will be b root d by 2. This is b root d by 2. So this is the last term. So when you consider b by 2 and this b root d by 2, when you take b out from these two terms, the remaining term will be 1 by 2 plus 1 by 2 root d. So the same thing. So you can write it as a, when we take b from these two terms, you can write it as b into 1 by 2 plus 1 by 2 root d. Because when you compare these two terms, you can write it as b times 1 by 2 plus 1 by 2 d. Then compare with this, you can write it as a plus b times this one. Then the remaining term will be minus b by 4 plus bd by 4. Okay, now this is of the form 1 into minus b by 4 plus bd by 4 plus this 1 by 2 plus 1 by 2 root d times a plus b. Okay, that means we have written this alpha into the second term, alpha into half plus half of root d as 1 into this, and this base element into a plus b. So we have alpha can be written as a plus a into 1 plus b into this, and the second term can be written as this manner. So we have the second term is alpha into 1 by 2 plus 1 by 2 root d. These are the base elements, say y1 and y2. So that can be written as a into x1, b into x2. Similarly, this minus b by 4 plus bd by 4 into 1, that is what we call x1, and a plus b times this 1 plus 1 by 2 plus 1 by 2 root d. Okay, now you can write the matrix, transition matrix, as here the coefficient is a, here the coefficient is b, here the coefficient is minus b by 4 plus bd by 4, and this term will be a plus b. When you evaluate this determinant, you can write a square plus ab, and this will be minus of minus b square by 4, that is b square by 4, and minus b square d by 4. Okay, in fact this is a plus b by 2 whole square minus b square db square by 4. This is in fact the norm of alpha. Okay, when you consider modulus of this, you can write modulus of this. Now you can say that in any case, if D is congruent to 1 mod 4 or D is not congruent to 1 mod 4, we can get this determinant of this is equal to modulus of n of alpha. So this is defined as cardinality of O by ideal general by alpha. So in any case, we can say that cardinality of O by ideal general by alpha is same as cardinality of n of alpha. This is what we have proved here. Cardinality of O by ideal general by alpha is equal to modulus of n of alpha. But we know that this quantity is always less than or equal to 3. Okay, so that is norm of n of alpha is less than or equal to 3. If in the case when D is congruent to not congruent to 1 mod 4, we can get the norm as a square minus db square. Then modulus of this quantity is modulus of a square minus db square, and we have proved that this is always less than or equal to 3. But in our case, D is less than minus 11. In this case, B will be 0 immediately, because this D is greater than or equal strictly less than minus 11. So this never be less than or equal to 3. So D must be 0. Then the only possibility is for this a square. Mod a square is less than or equal to 3. The only possible square of a number a square is less than or equal to 3 is 1. Then we have a is equal to plus or minus 1. This is the only possibility. In case when D is congruent to 1 mod 4, you can write this element as capital A by 2 plus capital B root D by 2. We already discussed this expression before, where this small a is equal to capital A by 2 in the case when A plus B by B root D. Then B is equal, small b is equal to capital B by 2. So in this case, the norm a square minus db square is a square by 4 minus db square by 4. This is always less than or equal to 3. This means capital S square minus d capital B square is always less than or equal to 12. So this should be less than or equal to 12. But whenever we choose values like minus 11, minus 13 and so on, we can say that this quantity, this d is less than minus 11. So we can choose d from these numbers. So the first possibility is d is equal to minus 13. If d is equal to minus 13, this would be greater than 12. So this statement implies that b is equal to 0. Capital B is equal to 0 means capital A square. A square is always less than or equal to this number 12. That is modulus A square less than or equal to 12. This implies A square will be both are same. Modulus A square is same as A square. So A square will be 1, 4, 9. These are the only possible squares less than or equal to 12. Then A must be plus or minus 1, plus or minus 4, plus or minus 2, and plus or minus 3. These are the only possibilities. If we choose plus or minus 1 or plus or minus 3, you can get this is 1 by 2 and 3 plus or minus 1 by 2 and plus or minus 3 by 2. Then when you evaluate the norm never be an integer, because we know never be an element of z. We know that this norm alpha is always a rational integer, is an element of z. So in order to get this norm alpha as an element of z, we need to choose this. A capital A should be plus or minus 2. In that case, we have A is equal to plus or minus 1. So the only possible values for this A is plus or minus 1 and B is equal to 0. In that case, when we evaluate the norm, we can get norm modulus of norm of alpha is always 1. Whenever norm is modulus of norm is plus or minus 1 or modulus of norm is 1, we can say that this alpha is a unit. Okay, so that is a contradiction because we have chosen alpha as a non-zero non-unit with a minimum phi value, phi of alpha. So this contradicts the choice of alpha. So this shows that Q of this ring of integers of Q of root D is not a Euclidean domain. Okay, so we have proved that whenever D is equal to -1, -2, -3, -7, -11, -13, minus then we have square for integer -15 and so on. So for all these values up to this uh, ring of integers of Q of root D, up to this value, we have Euclidean domains. From this we have or all the ring of integers of Q of root D in this category are not Euclidean domain. Okay, so we have classified quadratic Euclidean fields for all D equal to -1, -2 or negative D. Okay, so the only possible Euclidean domains are this. So in this case, the Euclidean evaluation, one of the Euclidean evaluation function is norm. So this is what we called norm Euclidean domain. Okay, so these are called norm Euclidean domain, and rest of them are called are not Euclidean domains. Next is theorem 4.19. We will not prove this theorem in our syllabus. This is out of our scope. But the statement is very important. The ring of integers of Q of root D for positive D is non-Euclidean if and only if D is equal to these values. Okay, this is the study of the Euclidean domain, quadratic Euclidean domain corresponding to D as positive numbers. So it is already stated that we cannot prove this theorem. Here, a good survey of the problem and related questions with references given in this book. So this is one of the research problems in algebraic number theory to evaluate the Euclidean domain corresponding to a given D. So this is up to the module end of module 3. Next we will discuss module 4. Start with chapter 5. In chapter 5 there will be a study of ideals. Okay, thank you.